Okay, today I want to do consequence 4 from relativity, consequence 3 and 4 I should say. I want to remind you, only works for non-accelerating frames of reference. The only invariant is the speed of light. We saw that time slows down when we're viewing moving frames of reference. We saw that length contracts when we're viewing moving frames of reference. I want to make sure you remember LO stands for proper length. This guy on Earth would measure the proper length between the two planets because he is at rest relative to those objects. L represents the length viewed by somebody in motion relative to what's being measured. So if we were looking at the ship, this guy now measures the proper length. This guy now measures a different length, a smaller length. Length, we saw, goes to 0 as the speed goes to the speed of light. Time stops, length disappears. Okay, consequence number 3, I'm just going to go right into it because the derivation's more than we can do through this method of teaching. So this is the formula. And what this formula tells us is that it's not just length and time, but it's also mass that changes when we view the mass from a different frame of reference. So the person in this ship would see the elephant with a certain mass. The person on Earth would see the elephant with a different mass. And it turns out that the person who is at rest relative to the elephant measures the proper mass, hopefully that's not a big deal, but the other person views a greater mass. So unlike time and length, which contracted or dilated, mass increases. And because of that, the radical is on the bottom of the fraction. So the guy on Earth would see the elephant with more actual mass than the person who is standing right near the elephant. So proper mass is measured by somebody in the same frame as the thing being measured. This guy would measure the proper mass of the elephant, the proper mass of himself, and the proper mass of the spaceship. This guy would measure the proper mass of the Earth, or himself, or anything else on the Earth. Okay, so which one is proper and which one is not? The proper is the one that's measured by somebody in that frame of reference. Okay, and this is again how the formula looks. This time the graph looks like this. This is showing us that mass doesn't decrease, it increases, as we could tell from the fact that the fraction was on the bottom. It was on the denominator this time. So the mass approaches infinity as your speed approaches the speed of light. Okay, so if we were looking at this ship, as it travels past us, the faster it's traveling, the heavier the ship would look. And if it was traveling at the speed of light, this thing would have a mass larger than the entire mass of the universe. The mass of the ship approaches infinity. Okay, now we want to talk consequence 4. And consequence 4, you're going to figure out on your own. We're going to be looking at the kinetic energy of the ship. And I want you to realize that the kinetic energy is going to be different as viewed from these two different frames of reference. For the guy in the ship, he's not going to even know his ship is moving. Okay, so he's going to think that his frame of reference is at rest. And he's going to think he has no kinetic energy. For instance, if I was to look at this Rubik's Cube, I would think it has no kinetic energy. But realize it's moving. The Earth is moving around the sun. The Earth is rotating. But from my frame of reference, it appears it's at rest and it has no kinetic energy. So kinetic energy will look different from different frames of reference. So you're doing the guy on Earth. How does he see this kinetic energy? It's going to be different from what we saw earlier in your study of physics. Okay, so here's the scenario, and this is all on a Google slideshow that you're going to fill out as you go. The scenario is that you are on Earth. You see a spaceship traveling by you. The proper mass of the spaceship is 10,000 kilograms. The ship is going to travel by you at a variety of different speeds. For step one, what you're going to do is use the new formula for mass. And you're going to figure out the mass of the ship as viewed from the Earth when the ship is traveling at 100,000 meters per second. Yes, a very high speed for normal circumstances, but kind of low when we're thinking about the speed of light. Show your calculation below. So when you show your calculation, make sure you write it all out. Again, the proper mass goes up top. Your fraction goes down the bottom. Your radical goes down the bottom of the fraction. We said the ship had a mass, we already had that, of 10,000 kilograms, so make sure that goes in for proper mass. And then the velocity is 100,000, plug that in here. Be careful, don't mess these up or you won't be able to figure out the conclusion today. And then get the mass as viewed from Earth. Then you're going to find the difference between that mass that you just calculated and the proper mass. That will be called our change in mass. What is the difference between the mass viewed by the guy on the ship and the mass viewed by the guy on Earth? Show your calculation. Again, start with the equation. Show the numbers you plug in, your answer, and your units. Okay? Put the picture right on this slide. Now you're going to calculate the kinetic energy of the ship as viewed from Earth. So kinetic energy equals 1/2 mv squared. Make sure you use the mass viewed from Earth. The one that you calculated in step one. Use the speed of the ship and make sure you're doing it in meters per second. When you make your calculation, that kinetic energy will come out in joules and expect it to be a really large number. Okay, for step 4, you're going to fill out your data table. The one for 0 speed should be easy. The spaceship should have a mass of 10,000. That's the proper mass. There is no difference in mass, and the kinetic energy should be 0. Then you want to do the one you just calculated. So what mass did you get here? It's going to be real close to 10,000, so don't round anything. What's the difference in mass between the 10,000 and what you calculated? And then what is your kinetic energy? Should be a really large number. You're showing all those calculations on the previous slides. You do not need to show them for all these other trials. You are then going to repeat the process that you went through for all of these different velocities. You're then going to plot out a graph using my graphing program of the change in mass versus kinetic energy. So this is your X, this is your Y. When you graph this, you're going to get a really important relationship, and this is consequence 4. Okay? So plot out your graph using my program and then paste it onto this program and get rid of the graph that's already here. Okay, step 6, I want to see what you can figure out. Please do this on your own. I will not mark off if you get it wrong. I just want you to try to figure out what the heck that relationship in step 5 is telling us about the change in mass and the kinetic energy. If everything goes right, you should get something that is really, really important. All right. Anyway, guys, you have until Tuesday at midnight to get this done. So best of luck.